This short tutorial, I'm going to show you how to compute the attention values step by step, and this is based on my previous whiteboard tutorial where I explained the theoretical concepts on how to calculate attention values. So let's go ahead to get started. We are going to write a function that takes a sequence of text and length weights. If you want to understand all this, maybe you can watch the previous video and compute the scaled dot product attention. The function should take in the following parameters: WQ, the query weight matrix; WK, the key weight matrix; WV, the value weight matrix. Text is the sequence of text. Alright, so as you know, the first thing we need to do is to convert our input sequence to embeddings. So we are going to take this and convert this text. Every good boy does fine. We are going to convert it to embeddings. So I'd like us to write a function that actually takes a sequence of text and produces the embeddings for it. So I'm going to say function that's, so we're going to write this function and it's going to be based on existing tokenizer, because we'll need a tokenizer for us to be able to compute the embeddings, because the first step has to do with tokenizing the text and then computing the embeddings. So we are going to use an existing model. So it's going to be from transformers import. We are going to need auto tokenizer, and we're also going to need auto model transformers, right? Okay, transformers. Okay, so the next thing we want to also do, we are going to be needing torch. So I'm going to also import torch. Okay, great. Let's now write our function def. I'm going to call it get embeddings. Get embeddings, and it takes a sequence of text, and then we have the create a tokenizer and the model. Now we are not going to worry about getting the tokens. Of course, you can also do that. We are simply going to get the embeddings. So for that, we are going to get the inputs to the model is going to be tokenizer and provide the text, and is going to return PyTorch tensors. The output is going to be model input. So the model is like just a normal neural network model, but it has an output layer that provides us the embeddings, and that is why to get the embeddings we are going to call the outputs dot last hidden state. Right, so this gives us the embedding values for this input text provided here. If you want to try it out to take a look at how what comes out, let's just say embeddings is equal to get embeddings text, and we are going to just print embeddings. It's going to just be a lot of numbers, but let's just see how it looks like. So if I run this code right now, you can see that we have Torch has no attribute embeddings. So this is not Torch with embeddings, but just embeddings. So if I run it, you can see we have all these values. So these are the embeddings. Now, one thing I want you to realize is the shape of these embeddings. The shape of the embedding is going to be 1 by 7 by 768, because for the auto tokenizer here, the length, the dimension of the embedding dimension provided by this model is 768. We have a batch size, a default batch size of 1, and we have our sequence length to be 7. So that's why the shape is going to be 1 by 7 by 768, 1 by 7 by 768. Sequence length you may think is 5, 1, 2, 3, 4, 5, but we also have an end of sequence token and also a beginning of sequence token, making it up to 7. So that's why we have this dimension here. So sometimes we can also eliminate this one. We can just take it out, and we have 7 by 768, meaning 7 is the sequence length, 768 is the embedding dimension. So if you visualize it as a matrix, we have 7 rows, 768 columns or features. Okay, so let's write the second function. So this second function to perform scaled dot product. This function is going to take WQ, WK, and WV, and it's going to return the scaled dot product attention. So the first thing we are going to do here is what? Is to derive the queries, keys, and values. And how do we derive the queries, the keys, and the values? we are going to map the embeddings to QKV using the weight matrices, right? So the first thing we do is to get the embeddings. So I'm going to say embeddings is equal to get embeddings text, okay? Okay, so it doesn't give me IntelliSense, so I'm going to just count. Oh, it does, okay. Okay, so what we do here is touch.matmul. So when you do touch.matmul, it also performs a dot product of embeddings.wq. So this is the same as embeddings.wq, and this is exactly what we have as part of the scale.product attention formula. Now the next thing is going to be to calculate the attention scores. So let's compute the attention scores. So attention scores is equal to touch.matmul, and we have q dot transpose k by the dimension 1, 2. Now I'm going to scale it separately, right? So I'm going to just, so now what we have is the attention scores. The next thing we want to do is I'm going to say scale the attention scores. And already I explained this in my previous tutorial. You're simply going to divide the attention scores by the square root of the embedding dimension, which is actually the square root of 768. I'm going to say scaled attention scores is going to be attention scores divided by square root of the embedding dimension. The scaled attention scores is attention scores divided by touch the square root of touch the tensor embedding dot shape 2. So in this case, shape 2 is 768, right? 0, 1, 2. Okay, great. So once we've scaled it, we are going to now calculate or compute the attention. And it's quite easy. So we have the attention is equal to touch.matmul scaled attention scores times v. Okay, so this is about how the function looks like. Now let's try out this function. Let's try out to see this function. So if this function works as expected, test the scaled dot product attention. So first we are going to initialize some random weights. WQ is equal to touch dot run. So we are trying to create the weight matrices to be a vector of 768 by 768. So the second parameter to this should be 768 as well, because the first parameter, this should be the length of the. So the first parameter will be the length of the matrix, the length of that is the number of how will I put it? So the number of rows in the weight matrix, and the second parameter is the number of features. So generally, the number of features should be exactly the same as the number of features in the embeddings. So we have this right now, and we are going to derive the embeddings. Embeddings is equal to get embeddings for this text. So we have the embeddings right now. So attention is equal to scaled dot product attention, and we have the attention dot shape. But we are missing out something, right? So when we calculate the attention scores and we scale the attention scores, we are going to calculate the attention weights. So we are going to compute the attention weight. Simply, we compute the attention weight by passing the attention scores through a softmax function. So this is something I forgot. So let's just do it right now. So attention weight is equal to touch the softmax scaled attention scores along dimension -1. So we have our attention weight, and from there we calculate the attention, and then we return the attention. Now we are testing out this function, and if I take out this, let me just run everything. So let's run this one. Now let's run this, and we can see that we have the attentions printed out, right? What I want you to take note of is the shape of the attention. The shape of the attention should be the same as the shape of the embeddings. So let's just check that and see if we got it right. You can see that the shape of the attention is exactly the same. So what it means is when the embeddings is going into the attention block, The same shape of the data of the embeddings going into the attention block should be the same as what comes out of the attention block. So the attention values calculated is more or less like the embeddings enriched with contextual information. And that's why we have the same shape. I did explain this in my previous tutorial where I did a whiteboard section explaining the theory, the mathematical formula behind attention computation. So this is basically solution to exercise 1, computing attention values. This exercise is in the textbook as the Attention Architecture Demystified, which is available possibly in 2 weeks from now. You can check the link in this video. So I'm going to be stopping here. Remember to subscribe if you've not subscribed to my channel. Also support me on Patreon. Buy me a coffee. You see the link there. And also there's a link that says thanks. Click on it and also give me some support in this channel. If you have any challenges whatsoever, please leave me a comment in the comment box below. Connect with me in my social network profile and also be checking my channel from time to time for new videos. So we see in the next part.